Okay. So good afternoon, everyone. Welcome to lecture 9 on the course Data Structure and Algorithm. So in the previous class, we have understood the logic and algorithm of binary search method, and we have seen a demonstration of the program implementation of binary search. Okay, and in today's class we shall be discussing about the performance comparison of linear search and binary search towards a same problem. Okay, so uh, we have seen that earlierly and understood that linear in binary search you require an assumption that the data structure elements, okay, are to must be of sorted order, and in case of linear searching there is no such assumption required. Okay, so I have shared my screen, hope you can see my screen. So first thing we want to address today, uh, very important, that is question 1. Question 1 is derive the order of complexity of binary search. Okay. Now let's understand the binary search once again. Consider an array like this: 3, 4, 5, 6, 7, 8, 9, 10. 10 elements are there, an array of 10 size. Okay. So for example, this is your index number 1, this is your index number, let's say n, and n by 2 means, for example, this is your n by 2, index number n by 2. So, and dot 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 dot. In our case, n equal to 10, then it will be 10 by 2, 5. So 1, 2, 3, 4, 5. Okay. So what we are doing, that is, we assume that this array is in sorted order, in ascending order, sorted in ascending order. So then we are finding the middle position with respect to the start index and the last index, 1 and n, that is n by 2, for example. Okay, okay. So now, after finding the middle position, let's say this position, we are comparing the user given value with the element present at this index, at this middle position. Okay, so if that user given value is x and that is greater than this element, let's say suppose a of n by 2, a suffix a by 2. So this is a1, this element is denoted as a1, this element is denoted by slow an. Okay, so similarly this element is denoted by a n by 2. So if we have that x greater than a n by 2, then x is not possible to lie in this range. Rather, we have to go further chain in this subpart of the overall array. Okay, so ultimately, before this checking, Okay, so how many number of elements we have here we were considering before this comparison, x greater than a n by 2 or x less than a of n by 2, before doing this comparison, how many elements we were considering for our binary search,
Sorry, n elements. N.
and that is n, starting from 1
Yes,
to
sir.
n, all the elements. Okay, so initial we can formulate like this. So at iteration 1, the number of elements considered is equal to n. Now, when iteration equal to 2, 2 means we were comparing x greater than a of n by 2 or x less than a of n by 2 or x equal to a of n by 2. After comparison, what we are doing, we are rejecting some part of the array and accepting the remaining part of the array. And what is the number of elements present in the accepted sub part of the array? Okay, and that is roughly, we can say that, okay, almost half number of elements we are rejecting. Okay, so for example, in this more precisely what it will be. So if we have total n number of elements, okay, and let's say n is odd, okay, n is odd means 9, 7 or 13 like that. So its middle position will be n plus 1 by 2. That is your middle position. You may apply, you may not apply floor function. It will ultimately come as an integer value. Okay, so n plus 1 by 2 is the middle value, middle index. So in that case, n plus 1 by 2 minus 1, that is the index of immediate previous element with respect to the middle one. If this is the middle position, then immediate previous position will be n plus 1 by 2 minus 1. So that is n minus 1 by 2. And immediate right index to the middle, okay, its index will be n plus 1 by 2 plus 1. And that is your n plus 3 by 2. So this is the index.
স্যার এটা অড নাম্বার অফ এন এর ক্ষেত্রে তো?
হ্যাঁ হ্যাঁ, আমি অড সুবিধার জন্য বলছি, ইভেনের ক্ষেত্রে
আচ্ছা
একই রকমই আসবে, একটু 19-20 হবে। ওকে,
ওকে
right, so n plus 3 by 2. Now how many elements we are considering in the next iteration? So the elements which are being considered in the next iteration, assuming that the x is greater than a of n by 2, then start index will be n plus 3 by 2 and the final index will be n. Okay, so total number of elements n minus n plus 3, n minus n plus 3 by 2 and plus 1, and that is equal to see, this is 2n minus n, that is n, then minus 3 plus 1 minus 2. Okay, so minus 2, this is minus 2. So ultimately it is n by 2 minus 1. Okay, okay, and that is an obvious case because we are excluding this part. If you have greater than comparison or less than comparison, then you are excluding this part. So if you include that element to either half of the array, then it will be n by 2. As you are excluding, it will become n by 2 minus 1. So ultimately this is the more precise case. If n is odd, then in the next iteration you are precisely considering n by 2 minus 1 number of elements. If you consider either part, left part or right part, because as n is odd, so this is exactly the middle position, and with respect to that middle position, Okay, in either side you have equal number of elements, and that is n by 2 minus 1. Okay, so so now roughly what we can say in the next iteration, that number of elements considered is equal to n by 2. Okay, roughly. So we are halving the number of elements in the next iteration. Okay,
স্যার তার মানে নেক্সট ইটারেশনস গুলোতে n/4 n/, মানে এরকম কমতে
right,
থাকবে।
exactly. Okay, the number of elements are subsequently divided by 2 in iteration. Okay, and that is true. So similarly, in the next iteration, iteration number 3, what we will have, that number of elements considered is n by 2. Earlier it was n by 2. Now we are doing halving that. So n by 2 by 2, and that is equal to n by 4, which is in iteration number 3. Okay, and so on and so on. So till we have something at iteration number, for example, iteration number n, no, not n, iteration number I. Let's say we have one iteration number I where number of elements considered is equal to 1. Okay, is equal to what it will be. So for 1 it is n by 2 to the power 0. We may say that it is 2 to the power of 0. That is n by 1, that is n. Here it is
Sir, is
n by
it 2 to the power I minus 1?
right. Similarly, here we can write that it will be n by 2 to the power of 2 to the power of I minus 1. Okay, and that will be ultimately, even that will eventually be equal to 1. At the last iteration, we will come up to a single element that is equal to 1.
1.
Okay, right. So what we have from this,
Sir, 2 to the power I minus 1 কেন হলো?
yes, hello, please repeat.
স্যার বলছি 2 to the power I minus 1 টা কেন হলো?
See, from this pattern in iteration number, when iteration number equal to 1, we have n. N can be written as n by 2 to the power of 0. 2 to the power of
Yes,
0
sir.
means 1. So n by 1, 1, n. Next line, iteration number 2. Number of elements is n by 2. 2 can be written as 2 to the power of 1. So 2 to the power 1 means 2 to the power of n by 2 to the power of 2 minus 1. We can write like this,
মানে for
right?
different values of I, sir, we are calculating that
Right.
for it.
So then for iteration number 3, we have we have n by 4. So how can we write n by 4? That is n by 4 can be written as n by 2 to the power of 3 minus 1. And what is this 3?
I, sir,
This
I.
iteration number 3. So n by 2 to the power 3 minus 1. If it is 2, n by 2 to the power 2 minus 1, this case. If it is I, similarly it will be n by 2 to the power of I minus 1. Okay.
Okay, sir.
Okay, now what we have, so we have now that n by 2 to the power of I minus 1 is equal to n. is equal to n. So, or in the next line, we can write that n is equal to 2 to the power of I minus 1. Or in the next line, if we take natural, logarithm in both sides with respect to 2, we will have log of n will have okay. So verbally I'm saying that is with respect to base 2. So log n is equal to I minus 1. Okay. So in the next line, we have I is equal to okay. So see, so for a simplification, see, if we start this with 0, then it will be better. Why better? Because initially, uh, after successful completion of an iteration, means we are dividing the array into two parts. So if I start index with 0, then it will be n by 2 to the power 0. This is iteration number 1. Similarly, this is iteration number 2, and so on. I. Then it will be more convenient to you that it will become ultimately this is n by 2 to the power of I equal to 1, right? Oh,
Yes, yes.
what is happening? So this is okay, 2 to the power of I equal to 1. So we have here equal to 1. It will be convenient to all of you. If you start with 1, that is also not a problem. So I equal to log of n base 2, that we have. And what is the I? That is the iteration index, the last iteration index, okay, or the number of successful, the number of completed iterations. So one division means one iteration. So after when it becomes n by 2, when it becomes n by 2, see, now we can justify that thing. So iteration equal to 1, number of elements considered equal to n by 2, means whenever we are completing one iteration, we have elements n by 2. We are, if we complete two iterations, we will be having number of elements at our hand, that is equal to n by 4. So similarly, after the completion of iteration number I, we will have number of elements equal to n by 2 to the power of I, that is equal to 1. So how many number of iterations we are completing to come up to a single element 1, that is equal to I. So what is I here? So I in this case, so the number of completed iterations to achieve a single element in the array, in the array that is equal to I. Okay, so this number of iterations will give us the measure of time complexity. Okay, so time complexity T of n is equal to the number of iterations, that is log of n by 2. log of n base 2. Okay. So obviously this is the worst case scenario. So hence order of complexity of binary search is equal to P of n is equal to log of n. So even if you start with iteration equal to 0, then ultimately using polynomial theorem, we will come up to the result that time complexity of binary searching will be T of log of n. Okay. So this is a very basic proof of binary search complexity analysis, complexity function. Uh, okay. It's an analytical approach. This is what we have. In later case, when you will be studying about tree, binary search tree, BST, then it will be more convenient to understand, okay, and to prove more formally the complexity function of binary search. Okay. Okay. So if you have any question, you can ask me. Very easy to prove. Next, we are coming to second question.
স্যার
Yes.
সো স্যার আমরা যখন মানে ভাবুন স্যার কোশ্চেন রয়েছে ডেরিভেশনস অফ বাইনারি সার্চ কমপ্লেক্সিটি অ্যানালিসিস বাইনারি সার্চ, তো স্যার আমরা এইভাবে মানে ইটারেশনস গুলো দেখিয়ে দেখিয়ে তারপরে লাস্টে প্রুফটা করবো, রাইট?
Yes.
ওকে ওকে।
So, so now coming to another question. Compare graphically the order of complexity of binary search. So we have now, I mean, ready-made information of complexity functions of binary search and linear search. So linear search complexity is order of n, and binary search complexity is order of log n. So here, more precisely, we can say that it is in the order of log n. Okay. So linear search for n greater than or equal to 1, okay, and hence conclude which algorithm is faster. We can also do the same by we have already seen the algorithm of binary search in the last class. So if we take the algorithm, using that algorithm also we can prove that Tn will be equal to order of log n. Okay, so I have just shown you an easier process how we can come up to the result Tn equal to order of log n. So algorithm is faster to search an element, let's say 57, in a given list. That is, the list is 11, 2, 9, 13, or 57. The same example we have used earlierly for demonstration purpose. 25, 17, then 1, then 90, and then 3. 11, 2, 9, 13, 15, 7, 25, 21. Yeah. And by how much? So this question was appeared in the last year first class test. Okay. So let's discuss that question. Okay. So we know that uh, P of, let's say, BS for binary search. I'm using a suffix ds. So t of n is equal to order of log n. Okay, and t of linear search, we know that it is equal to order of n. So if we consider that TPS is equal to log of n, and T of linear search is equal to n. One exact time complexity functions we are considering. If we consider TBS equal to n equal to log n and TLS n equal to n, then we can sketch the following graph, right? Okay, the graph is looking like this. Okay, this is Tn. I am writing Tn means both TBS n and TLS n we are plotting. So this is TBS n. Okay, let it not write. You understand? Then let's say this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, and so on. Similarly here, 1, 2, 3, 4, 5, 6. Okay. Next, we can plot the graph of TLSN. Okay. So before that, as it's a straight line, so Tn equal to n. So it will pass through 1, 1, 2, 2. This is 3, 3. Okay. So now you sketch the straight line. So this is the graph of TLSN. Okay. Similarly, TBSN equal to log n. So log n, when n equal to 1, then log n will equal to 0. So at n equal to 1, the log n equal to 0. So it is intersecting the x-axis at n equal to 1. So when n equal to, let's say 2, n equal to 2, so log 2 base 2, that is 1. That means another point we are having here. Okay. Next, for n equal to 4, so log 4 base 2, that is 2. So when n equal to 4 means at this point it achieves this point. Okay. So when n equal to 8, then log n will be equal to 3. 8 means 5, 6, 7, 8. So this is the value. So 3 means roughly it is located here. Okay, now you got the picture how it will be looking like. Okay, graph. Okay, graph. This is your TBSN. Okay, okay. So this is fine. For n greater than equal to 1, we have sketched we have sketched both the graphs. N greater than equal to 1. So what we are asked, compare graphically the order of complexity of binary search and linear search. So we have compared we have sketched the graphs and hence conclude which algorithm is faster to search 57. So, so 57 means uh, just you have to assume that okay, you are given the sorted order list in case of binary search and the original array in case of linear search. So we are assuming that to apply our own algorithms. Okay, so while doing that, so you are just interested on what are the elements present in the array. We are not interested on that. What is the number of elements you are considering for searching purpose? So in our case, what is the n value? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we are given that n is equal to 10. So we are given the list of size 10, that is n equal to 10. So if n equal to 10, then using linear search, it will take how much time?
10 units.
ls, yes, in worst case scenario, it may take equal to 10 iterations to compare to search successfully 57 in worst case scenario. But as we are comparing 57, so 57 as is at the position 11, 2, 9, 13, 5. Okay. Okay. Let not be right like this. N where n equal to 10. This we can write. Oh, yes, right. Now, similarly, we can write what is TBLS. TBLS, BSM, sorry, TBSM, and that is equal to log of n, that is log of 10, and that is equal to log 10 by 2. This approximately comes as 3.22. Okay, 3.22 approximately. So if you consider function, floor function t of is equal to 3.22, then ultimately it comes as 3. Okay, so where is that point? So t, more specifically, TLS, this curve, TLS n curve is passing through the point 10 comma 10. When n equal to 10, TLS equal to n, so it is passing through 10 comma 10. And when TBS equal to log n, so when n equal to 10, it is floor function is 3 or exact value is 3.22. So it is passing through. So it's passing through. The graph is passing through. We are not doing any analytical calculation from the graph. We are trying to estimate. Okay, what will be the comparison difference between the two algorithms. Okay, so it is passing through 10 comma 3.22. Okay, so see, we will try to locate the points. So one point is this is 2, 3, 4, 5, 6, 7, 8, 9, 10. 10, right? So this is your 1 point. Roughly. So 1 point is located over here. Another point is located over here. So the graphs are passing through these points. And at n equal to 10, what is the difference between their time complexities? This gap. You know. So at n equal to 10, this TLS or linear search have taken this much number of iterations, 10 iterations. Okay, but for similar problem instance, n equal to 10, binary search have only taken just more than 3 iterations, or number of iterations can't be fractional. So floor function is 3, so it has taken only 3 iterations. Okay, so what is the difference between their difference between number of iterations taken by linear search and binary search graphically? So,
7 almost.
so that is
6 point something. 6.78.
so difference difference between number of iterations taken by linear search and binary search binary search, okay, is equal to, how can we get that? That is search, okay, so let's say give some variable, uh, p diff n p diff, and that is equal to pls pls n equal to 10 minus pbs n equal to 10. In the next line, that equal to, or okay, let me give equal to sign. So equal to 10, that is equal to 10 minus floor function of log 10. So in the next line, it is equal to 10 minus 3, that is equal to, or p diff is equal to 7 iterations. So they are differing by 7 iterations.
So binary
already,
search is faster by 7 iterations.
yes. Okay, so linear search is taking 7 more iterations compared to binary search, just graphically. Okay, so our conclusion is, binary search is faster algorithm than linear search by 7 iterations. Okay, so this is our answer to the question. Yes. Yes, anyone want to say something?
Sir, how can we apply the binary search if the array is not sorted already?
We see, whenever we are applying binary search, we are assuming that the list is sorted. So we have assumed that.
Okay, okay.
Okay. Any other question? I hope no.
The binary search is faster than linear search by 7 iterations. That is only for 10 elements, no?
Yes. More n will grow, more
Yes, sir. Yes,
binary.
sir. The number iterations will change. Number.
Right. This is in worst case scenario. See, we have not actually understood best case. There are three types of time complexities: best case time complexity analysis, worst case time complexity analysis, and average case time complexity analysis. So whatever we are discussing so far, we are discussing all those things with some limitation. Some limited knowledge we are actually discussing about. That is, always we are trying to understand worst case time complexity. But there is some best case and average case time complexity analysis, which are not same as worst case analysis. Okay, so that's why maximum it will take 7 iterations more than binary search. Linear search will take maximum 7 iterations more than binary search. It may not take the entire 7 iterations. It may take less than that, but maximum linear search will take 7 more iterations compared to binary search. That we are concluding. Okay. A rough idea, or you can say that. Okay, so I can actually, there is a short quiz 5. We have started very late due to the previous class. We started from 1:50, so I have some time now. So 5 or 10 minutes we have more time so to discuss. So I will wrap up at 1:45. So there is a short quiz 5, which will take maximum 5 minutes to solve it. Then I will introduce about linked list, and we'll wrap up and we'll close today's class at around 1:45. Okay, so I'm sharing the Google Meet, the short quiz 5 link in the Google Meet chat box. So I provided the short quiz 5 link on the chat box. Open it and submit by 1:40. It's 1:35 by 1:40.